Okay, so welcome everyone. Thanks all for being here. And so today, it's our great pleasure to have Wei Wu from NYU Shanghai, who will be telling us about the massless phases for the Wieland model in dimensions 3 or greater.
Okay, thanks a lot, Guillaume. Thanks for the invitation. And again, it was a pleasure to meet everyone, at least virtually. So today I'm going to present this work, joint work with Paul. Paul was defended from Coulomb, and now he is a postdoc working at Tel Aviv. So okay, so the talk is going to be primarily about the Wieland model, but let me just first mention there's a broader class of models called the Abelian spin model, which contain all of these examples, which basically means that this is a spin model. Each, the spin configuration is going to be some Abelian group. So there are the typical examples like the XY model, Wieland, the Zn model, Abelian lattice gauge theory, and so on. So we hope that the argument we present here can be also adapted to this broader class of models. So now let's start by gently introducing this classical XY model. So as we know, this is a spin model where each, spins on every vertex took value in some unit circle. So you can just parameterize the spin at each side by some angle theta. Now, so on any finite graph, you can write down what the Gibbs measure is. It's going to be proportional to the sum of the inner product of these nearest neighbor spins, or you write it as the cosine of the difference of angles. So this is the ferromagnetic XY model. The energy is maximized if the neighbors are tangentially aligned with each other. So this model has been used a lot to model novel low-dimensional materials like liquid heliums or high-temperature superconductor, and so on. So here we write down the Gibbs measure for any finite graph or finite subgraph of ZD, but there are well-known correlation inequality. Go back to the 70s, for example, this Geneva inequality that allows people to take the infinite volume limit of the measure. So basically, as you open more and more edges, certain observables have expectation which is marginally increasing, and therefore the infinite volume limit is going to be well defined. So this was also done by this group of people in the late 70s or early 80s. So now the XY model, of course, is a very classical model, but it has this e to the cosine of the angles. So maybe it's not such a natural function if you first want to prove something on it. So this motivates the physicist Wieland to introduce the following approximation. So the approximation is basically saying that if beta is large, theta I minus theta j are small, then you can sort of approximate this factor by a heat kernel on the unit circle. Okay, so it's just like it's a sort of a periodized Gaussian where you sum over all the possible integer valued windings. Now, if you just replace this e to the beta cosine by this heat kernel factor, you obtain what was called the Wieland model, which looks a bit nicer because now we have this heat kernel on the circle, and people also expect that they share the same kind of physics, but still it has a lot of there's still a lot of mathematical challenge because this theta is defined between 0 to 2 pi, so it's a periodic kind of potential, and it's highly non-convex. So it still presents a lot of mathematical challenge to understand the large-scale behavior for the Wieland model. So the XY and Wieland model are very special. Namely, they have a very special kind of phase transitions. So for typically people expect that one can mathematically characterize the phase transition by some kind of a broken of symmetry. Like for example, if you cool down a glass of water and it becomes an ice, so you got crystallized. So you break out this perfect rotation symmetry of the water. And but these models are very special. In particular, in 2 dimensions, the continuous symmetry, which is given by this, this direction of the spins, is not going to broken at any temperature, and it has this famous Kosterlitz-Thouless transition. And in particular, you can only characterize the phase transition by looking at topological defects, namely the vortices and anti-vortices of the model. So in one phase, they sort of want to combine and form the dipoles, and in the other phase, they are going to be quite spread out like a plasma. In dimensions 3 and higher, it's got to be different. So you do expect the symmetry breaking when the temperature is very low. So you expect the spins tend to align with some preferred direction. But because of the continuous symmetry, on top of this preferred direction, there will be some kind of a macroscopic fluctuations, given by some kind of spin waves. Okay, so this is, or in physics, tend to call these things Goldstone bosons. So let's be a bit more precise. So in particular, phase diagrams, we believe is that in 2 dimensions, there is a critical temperature, which is 8 pi. Now, at any temperature, there won't be any preferred direction. But when you cross 8 pi, you go from an exponential decay of correlation to the Kosterlitz-Thouless phase, which is characterized by a power law decay of correlations. Dimensions 3 and higher is going to be the difference. So there is a critical beta, which we don't know, exact value. But then as you cross this critical beta, you go from the exponential decay to the long range order. And in the long range order, we expect that this fluctuation is going to be on large scale behave like a massless free field or the Gaussian free field. However, mathematical rigorous work is still far from being complete. So we basically only have results at quite small beta or quite large beta. So in the small beta side, there were this result by Eisenman and Simon, which says, okay, it's basically comparing the XY to the Ising model, which says if the beta is smaller than 2 beta Ising, you have the exponential decay. For large beta, so in 2 dimensions, there were this Kosterlitz-Thouless transition proof given by McBride-Spencer and Froelich-Spencer. So so they gave different power law upper and lower bound of the 2-point function. So we know it behaves power law in this region when beta is very large. In dimensions 3 and higher, first of all, there was this infrared bound technique in the 70s, which shows when beta is big, we have a long range order. And then on top of that, there were more precise results in the 80s by Froelich and Spencer, for example, which shows, okay, we have a long range order, but now if we subtract S with the magnetization, so you can look at the truncated 2-point functions. So this work by Froelich and Spencer in the 80s gave bounds, well, upper and lower bounds for the truncated 2-point function. And the work I'm going to present today with Paul is that we obtain precisely the asymptotics of the truncated 2-point function in this dimension at least 3 and low temperature regime. Okay, so let's be a bit more precise. So in this infrared bound technique is very helpful. It was introduced in the 1970s, and it it basically can bound the non-zero Fourier modes of the 2-point correlation functions. So in particular, in this context, they were managed to show that this limiting 2-point function has a lower bound, which is 1 minus the Green's function at 0 divided by beta. Now, in dimension at least 3, we know the Green's function is finite. So if you took beta large, you have the positivity of the limiting 2-point function, which means long-range order. Okay, now it would be very natural to ask what happens in this case. Like, what can you say more precisely about the 2-point function? So if you ask this to a physicist, so this is an approximation that the physicists would always like to do. It's called the spin wave approximation. So basically, when the temperature is very low, and so you, first of all, you would expect that these angle difference are going to tend to 0 because they are more likely to be aligned. And then the physicists can just replace the cosine by a quadratic function in this case. And then you basically treat these XY or the Villain model like a Gaussian free field. So if you do that, you can do explicit calculations, right? For example, the 2-point function, you can just calculate explicitly using this Gaussian computation. It gives that in 2 dimensions, you have a power law decay, which is x to the minus 1 over 2 pi beta. And then in dimensions 3 and higher, we have the 2-point function behave like a constant plus another constant divided by x to the minus 2. Okay, so this spin wave approximation, it basically sort of give the right qualitative behavior of the low temperature correlation function, but they were not precise. Okay, in particular, this exponent, this power in the 2 dimension predicted this way is not correct. And the constants predicted in the 3 and higher dimensions are not correct if you use a spin wave. The reason for that is that by treating these rotator models as a Gaussian free field, the spin wave basically ignores the vortices. So we know that on each face of the graph, right, you could have these topological defects like the vortices. Sometimes you have a vortex, sometimes you have an anti-vortex. And in fact, they will present there and they will change the large scale statistics of your model. So, okay, so there is some very non-rigorous argument by Kosterlitz and Thouless, which I won't go into, but they think that they can sort of separate out the contribution from the spin wave and the vortex. And basically what they believe is that this, vortex and anti-vortex are behaved like neutral Coulomb gas. So if we believe in that, so okay, based on these beliefs, they made the following conjecture is that basically the presence of the vortices will change your exponent in 2 dimensions. So in 2 dimensions, if you're above 8 pi, you expect power law decay, but the exponent will be different and will be corrected by the vortices. So McBride and Spencer obtain an upper bound, which is this Gaussian upper bound. Okay, so this is what you would expect from the spin wave calculation, exactly this exponent. And has been, okay, this bound has been improved last December by Garban and Sepulveda. So what they can do is they can also adding a correction to this Gaussian power term. So you get something which decays strictly faster than what you have for a Gaussian free field. Now, on the other side, there were this famous work by Froelich and Spencer, which uses an elaborated renormalization argument and shows that if beta is, at very low temperature, you expect a lower bound with a different exponent. However, this different exponent as beta go to infinity would be getting closer and closer to beta in this sense. So in some sense, combining this, you could say that this Gaussian spin wave prediction is only true, at beta equal to infinity in some sense. But for any beta which is finite, it still remains to be an important open question to prove this two-point function behave like a power law. Now, what happens in 3 and more dimension is that we believe that if you look at the two-point function, so there is first term, which is just the magnetization squared, and then on top of that, there's this truncated correlation function, and you expect it behaves like the correlation function for a Gaussian free field. So it's like you have 1 over x to d minus 2, but the constant here is going to be not the one that you obtain from the spin wave computation. It's going to be something which is also corrected from this vortex configurations. And then you have a lower order term. So, so in the 80s, so Froelich and Spencer obtained both upper and lower bounds for the two-point function. So the upper bound is, again, this is Gaussian type upper bound. And for the lower bound, it's going to be more and more precise as beta go to infinity. So the other thing people studied in the 80s, something called the transversal spin wave. So what this quantity means is that let's say you put your model in the finite box and then put all boundaries pointing in one direction. Let's say the this E1 direction, and then you look at the infinite volume Gibbs state. Now, in that case, you could look at the vertical component of the spins. So they form some kind of what they call transversal spin waves. And in this work, people also obtain the upper and lower bound for the transversal spin waves. It's bounded by 1 over x to d minus 2, but with different constant. Okay, so in the paper with Paul, so we were able to prove this conjecture in dimensions 3 and higher and very low temperature. So the two-point function, it behaves exactly as what we would expect. And we also have a corresponding result, which shows this transversal spin wave, the sine theta 0, sine theta x, asymptotically is a constant over x to d minus 2. So this indeed, you can observe that this this effective C is not going to be equal from what you calculated from a spin wave. But on the other hand, it's also going to be a very small correction of the this constant you calculate from the spin wave computations. Okay, so so in the remaining time, let me present how we are proving this result. So, so as we mentioned that the Villain model is a highly non-convex Gibbs measure. So in fact, we're not working directly with the Villain model. So there are a few steps. So the first step is that we're going to recall some of the rather classical duality argument back in the 70s and 80s to map the Villain model to a Coulomb gas model. And then we do renormalization. So again, there is this some known techniques of how you do the renormalization. In particular, you can use cluster expansion to further reduce this Coulomb gas model to some other Gibbs measure, which took real value. So it's like a random surface type of models. And finally, we're going to describe how we use techniques from PDE to understand the scaling limit of these random surface models. Okay, so for the first step, so this is going to be an argument which makes the prediction of Kosterlitz-Thouless rigorous. So, so the argument shows that you can, in fact, decouple the Villain partition function into a Gaussian free field times a Coulomb gas, which has this local neutrality conditions. So all the difficulty is going to be relying on how to understand this locally neutral Coulomb gas. So, okay, in terms of literature, so this observation was first made in the 70s in this paper of Jose Cardenov, Kirkpatrick, Nelson, but their argument is somehow only presented for the planar graphs, and the types of duality we're going to use is going to be based on the work of Froelich and Spencer in the early 80s. So, okay, so because we're doing dimension 3, unfortunately, we need to introduce some notation of vector calculus. So, or it's going to be a vector calculus on graphs. So we have the 0 form, which is just the function defined on Z3. We have 1 form, which is function defined edges. 2 form are like, for example, the vortices are 2 forms. So they are function defined on the faces. And then we have so on. We have the D operator, we have D star, we have the Laplacian defined in the usual way. Now, but in order to simplify all these things, so we don't actually write things into forms. So we're using some basic identification. For example, if you look at 1 form, it's defined on edges, but we can also identify, the 1 vertex with the 3 outgoing edges. And therefore we just write that in terms of a vector valued, like 3 component function defined on the vertices. So we can also do that for the 2 form. It's also going to be a 3 component function. And we can, based on that, define the usual gradient, divergence, curl, Laplacian operators. So the Laplacian basically took the functions to functions. It took the 3 component vector fields to 3 component vector fields. So the other the other thing which is quite crucial for this duality part is this Helmholtz-Hodge decomposition. It says that you can basically write any vector, you can decompose it into a potential field, which is then curl-free. Now, plus another part, which is divergence-free. And in fact, this is going to be an orthogonal decomposition, because if you look at the cross term, you integrate, you see by integration by parts, the cross term is going to be 0. So it's orthogonal, and in fact, you can just take the curl and solve what this psi is. It can be solved explicitly. Now, how does this work? So we start with this Villain model, and then we can first, exchange the summation and the product. So basically, M is going to be a 1 form, because on every edge, it has a 1 integer valued. So you have the sum here. You took the sum of M out. And then we're gonna split this sum M. So we're going to first sum over all possible vortex configurations. And then for each given vortex configuration, I'm going to sum over all the M, which leads to this particular vortex. So in this case, so we split the sum, and further we rewrite the second sum, because we can use this Helmholtz-Hodge decomposition to rewrite the M in terms of a potential field and the divergence-free field. The divergence-free field is going to be just a function of Q, as the previous formula tells us. So if we do that, we know this is an orthogonal decomposition. So if you just plug this back in the Villain model, you see that the square, after you expand it, the cross term will vanish. So you're just left with the 2 parts. Now, the first part, if you combine this, this theta, which is an angle between 0 and 2 pi, and this gradient of an integer valued field, you can rewrite the first part into an integral just on the real line. Okay, and this gives you an ordinary Gaussian free field. And the second part, if you rewrite it, it's going to give you a Coulomb gas. Now, which is, okay, it's also worth noticing that this condition on Q, which has the divergence of Q equal to 0, So this condition in dimension 3 and higher is really a local neutrality constraint. It means that, you know, Q and the Q's over all its neighboring faces have to satisfy some local constraint to have things canceled out. Okay, so this is going to be very important for the second part of the argument. Okay, so the second part is that we're going to rewrite this Coulomb gas part into a vector valued random surface measure, but then there's some price to pay. So the Coulomb gas, well, to us, the Coulomb gas is not so easy to study. Random surface model is better, but the price to pay is that the model, this mu beta is going to be a very complicated Gibbs measure, and the observable there we need to estimate is also going to be quite complicated. So so this part I'm going to follow this cluster expansion argument presented by Bauer-Schmidt. So first of all, you have a Coulomb gas. So this is the well-known Sine-Gordon representation, is that you can write, because this Gaussian free field has covariance Laplacian inverse, you can write it as some Gaussian free field expectation. Now, so this is for the partition function, but we also have something similar for the two-point function we want to study. So if we want to study the two-point function, it's going to be e to the I theta 0 dot minus theta x. So basically the same argument carries through, except that we will end up with a source at 0 and a sink at x. So this is, you know, extra that leaving to us. This is the sigma 0x function, which is the difference of the Green's function. And in all of these representation, this sigma 0x is going to be appearing in your expectation. Now, so now we do some kind of one-step renormalization argument. Is because you can just decompose your Gaussian free field into the sum of two independent Gaussian fields, such that the covariance adds up to what we have, which is beta lambda delta inverse. So if we do this splitting, right? So we think of phi 2 as a local field, which we integrate out. And if you integrate out this local field, you get some smallness term here. Okay, it's basically e to the minus beta 1/2 times the L2 norm of Q. So we know that if beta is big or the Q has a large support, this term is going to be very small. So essentially it favors just the small Q, which is like dipoles. And then we have the remaining expectation here. Now, because as we mentioned in dimension 3 and higher, this divergence Q is 0 is a local neutrality constraint. So you can basically, for every possible Q satisfy this, you can factorize Q into disconnected components, disjoint components, and then you with disjoint support, and then you do some summing over lattice animals, and because this guy is going to be small, this resummation works. So by some cluster expansion argument, you can in fact make the summation inside the exponent. So what you get would be something like this, where the z's are coming from this previous small factor, which is going to be very small. Okay, so this, what you obtain is the ratio of the two expectations, one with the sigma 0x there, one without. So, so then one can just write this whole thing as a big expectation with respect to some Gibbs measure. You just can use this trigonometric identity to expand this cosine A plus B, and you have something, right? So eventually, what one obtain is this complicated Gibbs measure and a complicated expectation. So, so the Gibbs measure is like this. Okay, so this is a 3-component. The field is taking value in vector value, so it has 3 components. And then we have this, which describes the law of the long range field plus this perturbation term. Okay, and on top of that, we have this particular expectation to estimate. So, okay, so this looks a bit horrible, but it's not that bad because when you write down what this mu is, you see that, so this term is not so great because it involves some long-range interactions, n times Laplacian, but for beta large, this is going to be a perturbation of the first term. The second term also, because z is small, so it's gonna also be acting as a perturbation. So eventually this is going to be a perturbation of some 3-component Gaussian free field. Okay, and moreover, because we have this mutual condition, it tells us that this term is basically only depending on the gradient of phi. So this is basically a measure on the gradient of phi, and it's going to be a perturbation of the Gaussian free field. Okay, so so we will be able to obtain very precise information of this of this long range of the large scale behavior of this model. So so just before just before telling you how this, we use the PDE technique to do that. So here is maybe let me just spend 1 minute in this heuristics, why this very complicated looking thing would give us the right answer. So it looks complicated, but one can, so for the back of envelope computation, one can make some assumptions. So the first thing is, when beta is large, the Qs, we know that they would favor nearest neighbor dipoles. So if we use this and we assume every Q is going to be concentrated on dipoles, you can simplify this observable. It becomes the sum of sort of the gradients. And if you further make the simplification that you think maybe the sine grad phi would be looking like grad phi, then you can just rewrite the whole summation into phi 0 minus phi x. And in particular, this, this whole Coulomb gas contribution can be written as a perturbation of GFF, and you have an observable like e to the phi 0 minus phi x, which in particular give you the behavior just like a constant plus a constant over x to the d minus 2. Okay, so when you combine the Gaussian free field contribution and this Coulomb gas contribution, this is what we do expect for the 2-point functions. Okay, so so we already did this first two, so this duality, renormalization, and now let me start telling you how we study this complicated looking Gibbs measure or the random surface models. So this is going to be based on some PDE technique. So first of all, it's going to be relying on this observation by Nadav and Spencer, who can link this certain Gibbs measure with elliptic PDEs with random coefficients. And then another important ingredient of us is this, the recent advances in the quantitative stochastic homogenization led by Scott, by John Christoph, and by Tuomo in this past few years. So okay, the measure we have, the random surface measure mu beta, is quite horrible. So let me first talk about the simplified case and how it works. So the simplified model is sometimes called the grad phi model. So we just have a very simple Gibbs measure. Instead of you have a Gaussian free field, which you have the grad phi squared, I'm going to look at the model which have a v of grad phi, but v is a uniformly convex function. meaning the second derivative is bounded from above and below, away from 0 and infinity. Okay, so this model, we can also easily make sense of the infinite volume limit of this model. For example, through the work of Funaki and Spong. So in the case that if you have V equal to Gaussian, then basically you can compute everything, right? So the correlation is gonna be given by the inverse of Laplacian. Now we have something more general, but we will see that some more elaborated version could help us to understand the correlation of the field, but through a more complicated operator than this. Okay, for that, we need to introduce this notion of the field derivatives. So this partial x is basically going to be a differential on the random field. So suppose we have f, which is a function on the random field. The partial x just means that you took the derivative if the phi of x changes. So you just look at the partial derivative of phi of x. So you can also do the formal adjoint of this operator partial x when you integrate out against the Gibbs measure. And you see that this adjoint is going to be explicitly given by this form when we have the Gibbs measure, which is sum of V of grad phi. Now, right, so this is, and then we can define this thing, which is sometimes called the Witten Laplacian. It's going to be the sum of this, which you can write down as this. Okay, so this delta phi is in fact so it's a self-adjoint operator. So you can check that if you integrate against the Gibbs measure, you can do this thing and you see it's self-adjoint. And probabilistically speaking, this delta phi is basically a generator of the so-called Langevin dynamics of your Gibbs measure. So, okay, so how does this help us? Is that, so here is the notion of, okay, what we call Helffer Sjöstrand operator. So it has two parts. One is this delta phi, which we just introduced. And then there is an ordinary elliptic operator term here. So all the gradients here are going to be just the gradients in the space. So they are just, discrete gradients on ZD. And then this A is going to be given by the second derivative of your potential, right? So in particular, when we have the assumption that V is going to be uniformly convex, then this one is an ordinary uniformly elliptic operator in ZD. But on top of that, we're adding another operator, which is infinite dimensional. Now, so we can solve the equation based on this new operator, which is the Helffer Sjöstrand operator, just as how we solve the ordinary elliptic equation, or just how we solve the Laplacian equations. And in particular, you can characterize the solution in some variational form, right? So for example, we can, as we all know, we can characterize harmonic function to be the minimizer of Dirichlet energy, but here you have something which is similar but more general. So this solution of this equation is also can be characterized by the minimum of this particular energy form. And in our setting where V is uniformly convex, this is also some kind of a convex function. Okay, so so the Helffer Sjöstrand representation says the following. So let's so if we have the Gibbs measure, we talk about this grad phi measure. Now we have functions of phi's. So we can in fact give a representation of the covariance of the function of phi's. So it's going to be like this. So you need to take the field derivative of capital F. So this gives you the small f here. You need to take the field derivative of capital G, and then you need to solve this Helffer Sjöstrand equation where L is this operator which has two parts that we just introduced. Okay, so this is the most general form, but a simplified form is that if you look at the covariance of phi x and phi y, this is going to be this expected value of the Green's function, where instead of g, you just have the delta function at y here. So that will be just this expectation of the Green's function. So from this, we see that, in order to understand the large-scale behavior of the grad phi model, it becomes quite crucial if we could understand, how this PDE behaves, right, on large scale. This is sort of a looking, sort of an infinite, is a PDE with some kind of infinite dimensional operator. But heuristically, so in order to show that the large-scale behavior of the grad phi model would be behaving like some Gaussian free field with some effective covariance matrix. So this is what we need to do, is that we need to look at the solution to the Helffer Sjöstrand equation looking like this, and to show that on large scale, this solution G behaves effectively like a solution to this constant coefficient harmonic equation. Okay, and in particular, we know that this constant coefficient harmonic equation, the solution is given by sort of proportional to the ordinary Green's function, which is like dimension 3 and higher, which is like 1 over x to the d minus 2, right? So in particular, a quantitative result would show that the solution of the Helffer Sjöstrand equation, if you compare this with the limiting constant coefficient equation, it's going to be small in the sense that it's much smaller than a typical order of g bar of x. For example, it decays even faster than 1 over x to the d minus 2. Okay, so this connection between Gibbs measure and homogenization, Gibbs measure, elliptic PDE, and homogenization. So this was first done qualitatively in the paper of Nadav Spencer, and also in some probabilistic form in this paper by Giacomi, Ola, and Spong. Now, in the joint work with Scott, we obtain quantitative rate of convergence of Helffer Sjöstrand equation to this limiting constant coefficient equation. And we were using that to prove this conjecture of the Funaki and Spong, which shows the regularity of the so-called surface tension, which measures the response of the energy to the tilt of your Gibbs measure. And in particular, you do need some quantitative rate of convergence in order to understand how this sigma is related to its finite volume version, and to obtain something quantitative. Okay, so of course, what we have presented here was just for the grad phi model, which is much simpler. So for the Villain model, it's much more complicated. So remember, this Gibbs measure is looking to be more complicated. So there are a lot of differences. But one thing is that we have a lot of terms which are non-local. So in fact, this ends up with your operator to be non-local. It has some long-range interaction. And the other thing is you have this phi, which is 3 component. So if you apply the Helffer Sjöstrand trick, you would get up, instead of one equation, you would have system of three equations, and certain estimate that people were used to for the elliptic equation no longer holds when you have a system of elliptic equations. So we need some extra input in order to resolve these issues. So the way we do is, in fact, we're borrowing some idea from PDE, in particular from the Sjöstrand theory. So the equation we have when we have this, three-component random surface model is going to be quite complicated. However, we can write down the corresponding L operator into two parts. One is the usual part, which came from this Gaussian free field leading term. And then there is this complicated mass, which come from all these smaller terms. But that's acting like a perturbation. So in fact, we can mimic the argument of the Sjöstrand theory to show that the solution with this complicated operator on large scale can be approximated well by the harmonic function, which just solves this operator. Okay, so in particular, we obtain what was called the C01 minus epsilon regularity, which means that the corresponding Green's function to here is almost as good as here with the epsilon worse. So for example, the Green's function to this operator is decaying like 1 over x to the d minus 2 minus epsilon instead of d minus 2. But you can make epsilon arbitrarily small if you're sending beta large. So this term is even smaller. Okay, and then we follow this. We can sort of building on this approach by Armstrong, Kusi, and Murat, because we have mentioned that there is this close connection between the solution and the minimizer of the energy. So we can just look at the corresponding energy and the dual form. So I'm not going to explain what there exactly is, but they are some kind of energy functional, which is defined in each cube or each finite domain, for example. And we can show that they are approximately subadditive, okay, which means these things do converge when you send the size of your domain to infinity. And now in order to obtain some quantitative rate of convergence, you would need some kind of mixing for these quantities, like the energy functional defined in one domain and another domain, which is far away, is going to be quite uncorrelated. So how are we going to do that? This is still going back to this perturbation theory, okay? So in particular, so these energies are defined in terms of the solutions in disjoint domains. So if we can show that the solution in one domain only depending very weakly on the field very, very far away, then that will be a good indication of the mixing. And in order to do that, we go back to this Helffer Sjöstrand equation, and we took further the field derivative to it. And then we obtain another equation, which is quite complicated. So this is something we call the second order Helffer Sjöstrand equation. So the partial y of this solution is solving another equation. Okay, it looks complicated. However, you would see that this new operator can also be separated into a leading Laplacian term plus a perturbation term. And this gives you that the solution to this equation is going to be almost behave like the solution to the ordinary Green's function. Then in particular, you obtain a power law decay of this field derivative of your solution. So this eventually helps us to gain the required power law mixing and to prove all the results about the quantitative convergence. Okay, so maybe I'm not going into more details at this point. So I appreciate being there, for your patience, and thanks a lot for the attention.
Are there questions for Wei?
May I ask a question?
Yeah, sure.
You mentioned the topology of vertices, which are natural sort of excitations for the
Yes.
XY model in 2 dimensions. Would there be an extension of this into vorticity lines of vorticity in 3-dimensional XY model?
Yeah, so
and do such lines play a role in the analysis? For example, intuitively, you may think that if the spins are oriented in a preferred direction as they are in low temperature, then vorticity lines perhaps may be lined up roughly randomly, but with biasing towards that direction.
well,
Does this
okay.
enter anywhere?
Yeah, it's a very nice question. Not at this work, I don't think, because we're looking at some kind of this, Gibbs state, which is infinite volume, and then all these, you see this, all the vortex Q are quite local, right? The divergence is 0, so it's sort of locally canceling out. So there's no conspiracy that leads you to a large vortex line. But there are questions you can do. For example, you can look at the Brownian type boundary conditions. Like, this, for easing, it's either described, you have a plus top and minus bottom. For this, it's gotta be more complicated, but just as easing, there is this phase transition in terms of the dimensions. So, so when the dimension is low, there's basically no non-translation invariance Gibbs state. So it's like easing, right? You have all these where you put plus minus this interface there in 2 dimensions. In easing is gonna be fluctuating a lot. But in 3-dimensional easing, you have this rigid interface in between. So therefore, there's this dichotomy in terms of dimensions. And for the XY, so there's this paper by Froelich and Pfister, which says that sort of the transition happens in, so they have a heuristic argument suggesting this happens in 4 dimensions. So, and basically the vortex line would play a crucial role there. And above that, they think there will be, there will exist non-translation invariant Gibbs state. So I would expect, in that situation, this vortex line is quite relevant.
Thank you.
Yeah, but here we still have this similar picture like 2 dimensions. So when beta is very large, we still have the Q forms dipoles. So they're sort of.
But actually, I guess in my mind, I was thinking more about 3-component spins. And then
I see.
When you have a preferred, when the symmetry breaking and magnetization in the preferred direction, I presume that the 1/x to the d-2 correlation has to do with the behavior of the transversal components. And they may, and there is room for vorticity for those, but the vorticity line may be fluctuating, but roughly proceeding in the direction of the symmetry or the broken symmetry.
I see.
I have to think more about this, but thank you.
Well, thanks. Yeah. So you think this 3-component, this vorticity line would also play a role to determine this constant over d-2? That's what you were thinking, or?
I do not know what role it would play in the actual analysis, but the picture of what kind of intuitive description of the nature of fluctuations, it may be useful.
Sure. Well, okay. Thank you.
Thank you.
Other questions?
Yeah, I wanted to ask your decomposition into this free field times Coulomb gas factorization. does that work for the XY model, or is this only for Villa?
So this complete factorization only works for Villain because you need a Gaussian thing. I mean, you really need a square in order to have the to have this cross term to cancel.
And that would work in 2D as well, right?
So that works in any dimension, yes.
So what's the difficulty
in 2D?
for applying your method in 2D?
Yeah, so the 2D is that this renormalization part won't work anymore. So because the Q's are not going to be like just factorized into disjoint support. So there's no simple way of renormalization that can gain you this convex Gibbs measure. So there were this elaborated work by Froelich Spencer, but they do things a bit differently, and they need this infinitely many scales, and what you end up with is not a simple Gibbs measure, but a mixture of many things. So that makes so that presently is a major problem for this argument work.
Yeah. So the first step would be to just understand the Coulomb gas into where this convexity is missing.
Yes, I mean, in some sense, you wouldn't expect the similar picture, right? When beta is big, you do expect dipoles. And when you have dipoles, you should have some kind of convexity. So it, yes, yeah, but there's no this particular nice way of just relate this to one Gibbs measure at present. Thank you.
More questions? Okay, let's thank Wei again and for the great talk.
Thank you very much.
And I'll stop the recording.